Here's a video here which will give you the general ideas of what dielectrics are used for. Dielectrics are often used in capacitors here. Let's just see what their application is. So what I've drawn here is a charged up capacitor. I have a metal plate here and a metal plate here. I've connected to some voltage source here. I've got positive charge flowing onto this plate, negative charge onto this plate. I maintain this spacing between the capacitors right here, and of course an electric field appears in between the plates like that. So the question then becomes is what happens then as I start to increase the capacitance here. We know right off that for the parallel plate capacitor, the capacitance there is epsilon naught A over D, something like that. Okay. And then the amount of charge that can flow onto the capacitor plates here is equal to CV. So if I want to get more charge on the capacitor here, well, I can just, maybe there's a knob on a power supply in the laboratory or something like that. Maybe I have it set, here's 0, 1, 2, 3, 4. I can just start turning up the knob, maybe up to 4 like that, get more voltage on there. And of course, if you do that, you will get more charge on the plate. So if I sort of increase the voltage here, I'll get more positive charges flowing onto this plate here, more negative charges flowing onto this plate here, and I can get more charge on there. And then I can just keep increasing the voltage even more and more. But eventually what will happen is if I do that, if I keep increasing the charge more than more, then increasing the voltage more and more, which results in more charge, then the capacitor very much will start to behave like a thunderstorm, where I have like the earth like this over here, instead I have all these storm clouds up here. And the reason why storm clouds sort of are turbulent weather is because the air molecules are moving around in a very violent way and they brush into each other. And so storm clouds start to acquire some charge here, like a net charge relative to the earth itself. And if the charge gets too high, then what happens? We'll get a big lightning bolt like this. Big lightning bolt comes down, the cloud is starting to discharge itself. But see, the capacitor will do the exact same thing. If you kept increasing this voltage and turning up, you get more charge on the plates at higher voltage, and eventually the capacitor here will just break down. There'll be a big spark across like this where the charge will actually jump the gap between these plates like that, and oftentimes it means your capacitor will also be damaged. Not always, but sometimes it means the capacitor will be broken as well. Okay, so you want to avoid that happening. Or if you really need more charge on the capacitor, but it keeps lightning bolting down like that, what are you going to do? Well, that's where dielectrics come in. So let's look again at the capacitor we're going to charge up, and we'll go a little bit less on the details in this case here. But when you have these two parallel plates here, no one said that what exists between the plates must always be air or a vacuum. No one said it has to be true. It turns out you can put things in between the plates. In a previous video, when we combined them in series, we actually stuck a piece of metal in there. Now, we're going to avoid metals in this case here. We want to put some non-metal in there, something that doesn't conduct. Because if we have the capacitor, which is all charged up like this, here it is all nice and charged, then we never want these plates sort of electrically to touch. That would discharge the capacitor, but we can nevertheless, insert something between the plates and avoid that happening. So if we insert something like this, say a big piece of plastic like this, or glass, or wood, or something that does not conduct here. This can be a non-conductor, or an insulator, of course. That's really what a dielectric is. It's a non-insulator. Non-conductor. It does not conduct electricity. So the question now is, if I insert something like this insulator in between the plates here, what happens in there? I'm just going to write insulator here because I keep getting my thinking backwards. So what's going to happen inside there? Well, we sort of discussed this in a video a while back, and that remember, there's no charge mobility inside these insulators here, but what these insulators do have in them are these little atoms here that sort of look like this. There's a bunch of little positive and negative sort of molecules or sort of constituents, however you want to think about them, that make up this material here. So over here, here's a little atom, here's a little atom, here's a little atom, here's a little atom here. And thermally, when the matter is in equilibrium like that, these little molecules are just pointing in all different directions. This one's pointing sort of vertical, this one's horizontal, here's another vertical one, this one's horizontal. There might be one diagonal like this here, because that's thermally what will happen here. But then what happens is when you insert it in between the plates of a capacitor, the electric field that exists between the plates of the capacitor actually will permeate the dielectric as well, because it always permeates the space between the capacitor plates like that. But now we have a piece of plastic in there. So here's the electric field like this, and I'll just draw a few arrows. Remember, out of positive and negative, the electric fields are generally pointing to the right here, the way I've drawn it. So the question now is, what happens to all these random thermally oriented dipoles, if you will, inside the insulator when the electric fields turn on? Well, they're going to orient themselves with the electric field. They can rotate a bit. And so, how are they going to rotate? Well, the negatives are going to try and align themselves with the positive plate, and the positive side is going to try and orient itself with the negative plate. So what you'll get then is a bunch of dipoles which are all aligned like this. Negative, positive, negative, positive. Now I won't draw too many. I'll just pretend that the dielectric here is sort of 3 dipoles thick because the drawing gets a little cumbersome here. But this is generally what's going to happen here. The dipoles, not perfectly, but they'll get all more or less aligned like this. In other words, the effect of this electric field here, it will polarize the dielectric. Polarize those molecules in there. And I'm going to draw a bit additional in here because I do like to sort of show where my dielectrics start and ends, or excuse me, my little dipoles start and end like this. So it looks like this, and like this, and like this. They're all sort of oriented in there like that. There you go. So that's sort of what happens when the dielectric is in the electric field. This thermal gibberish here of all different directions has now sort of been defeated on account of the electric field. The electric field is polarizing the dielectric, causing the dipoles to become aligned now. So I think we came over this before in a previous video, but we'll rehash it one more time. Now if you look at what you have here, is in sort of this deep inner material right here, in the deep insides of the dielectric here, you always have a positive which is really close to a negative, and a positive next to a negative, and a negative next to a positive, and a positive next to a negative, but only in that deep interior core. But if you look on the very edges here, sort of where these edge effects are, this negative is not really paired internally inside the dielectric with a positive. Sure, it's near the positive on the plate here, but it's not near a positive. There is no positive, say, right here, because the plate ends. Just like in this positive charge over here, for instance, doesn't have a matching positive because it's on the end of the dielectric also. So there's no matching one to sort of neutralize it. So the point here is that in the deep interior of the dielectric here, all of these charges here, inside here, they pair up and sort of neutralize each other. Electrically, they don't actually touch, they're still there, but they sort of appear electrically as if they've been neutralized. There's nothing in between. But notice this brown circle here, I've left out the ones on the edge right here. These do not neutralize, and these positives out here do not neutralize. So the net effect then is what we have is when we insert that non-conductor in between the plates of a capacitor like this, is we're going to get something that looks like this. So just a few things to draw here. Let me just get set up again here. Here's those positive charges again on this plate. Here's the negative charges on this plate right here. And then we'll go in and get that dielectric put in there. And remembering, though, that after the polarization is complete, the interior core of the dielectric is neutralized, but the edges are not. So on the dielectric surface right here, we have all these little negative charges that sort of didn't get this net neutralization effect. They can't find a partner because they're the ones that were on the very edge. Something like that. This is what it's going to look like. This is a fully polarized dielectric sitting inside capacitor plates like that. So now what effects does this have? Well, let's look at the electric fields. The blue electric field that I'll draw will be electric field due to the capacitor, and that doesn't change itself at all. It's sort of pointing like this. These are the electric field lines that the capacitor is presenting. The original ones that don't go anywhere, and it points sort of this way like that. There's the electric field due to the capacitor. So E field due to the capacitor is the one in blue there. And let's see, I guess I can use red once again here. Well, I'll use a slightly different color, maybe green here for the electric field inside the dielectric. You're like, what? What electric field inside the dielectric? Well, look at the dielectric. It has a separation of charges now. It has a bunch of electrons that get sort of net pushed up along its left edge, and a bunch of positive charges got pushed up against its right edge. It almost looks like a capacitor inside there. So there will be electric field, but the electric field, interestingly enough, points the other way. It points, remember, electric fields always point out of positives into negative, and the polarization of the dielectric is sort of the reverse charge situation as the capacitor. So where the positive charges on the capacitor are here and the negative are here for the dielectric, the positives over here and the negatives are over there. So the electric field is going to point in the opposite direction like this. And so what you get inside here is, look, so electric here, this is electric in the dielectric here. But look at what happens here. If you have an electric field pointing to the right in the capacitor and an electric field pointing to the left in the dielectric, there's going to be a net cancellation of the electric field. So if you want to know what the total electric field is in that interior region right there, the total electric field then is going to be electric field due to the capacitor here minus the electric field due to the dielectric. And no matter how you orient the system, the effect of the dielectric is always, here's the big thing here, dielectrics, they always reduce the E field, or reduce the internal oops, got to squeeze it on there, reduce the internal E field. That's the effect of a dielectric. No matter how you dice it up, you'll always get this polarization opposite to the actual charge on the capacitor here, which has the effect of reducing the electric field. Now, the dielectrics often don't get polarized fully like that, so you won't get a case where the electric field becomes zero, but you'll always have the subtraction in here. This will always be in here, and so whatever electric field the capacitor is presenting, if you just insert the dielectric, the electric field is going to go down. Now, why would this be important? Well, remember that if you have a capacitor like this, and you're trying to charge it up, you might have a maximum voltage that you can't exceed because you want to avoid that lightning bolt from occurring in here. As we discussed earlier in the video, you want to avoid like that noise of a lightning bolt in there. And the way you can do that is, of course, is to reduce the electric field inside the capacitor. So if you have this thing charged up maybe to 100 volts, and 100 volts is always giving this lightning bolt and ruining your capacitor, just take a big slab of glass and put it inside like that. And often what will happen then is the 100 here can probably go up to 180. And you won't have that lightning bolt effect because you reduce the electric field inside the capacitor here. And the amount of reduction is often called, I should probably just wrap it up here. Let me just get rid of it. That's why you want to do that here. The reduction is in the amount of a symbol called kappa, which sort of looks like a K. Kappa here. And kappa here is the dielectric constant. The dielectric constant. And you can look it up in your book. There's a table of them here. I don't have any in front of me right here. But there would be a table here. That's the material and the dielectric constant there. And you can see things in a table. You can look them up on Wikipedia. There's glass and wood and plastic. And something like even Teflon would be on there. And it turns out that then you just list these numbers for the dielectric. Like maybe glass, here's the table here. Glass, wood, plastic, Teflon, the material here. And the dielectric constant will be listed right next to it in there. And so you can actually look up the number for how much the glass, wool, plastic, Teflon, wood, plastic, Teflon, whatever, reduces the electric field. So like you can say like the E prime that happens when you insert one of these things here will be sort of the original electric field, the E naught, divided by kappa, because it reduces the electric field. And because the electric field goes down now, you can increase the voltage, and it turns out your ability to store charge, your capacitance goes up. So the capacitance, when you have the dielectric inserted, is often going to be something like kappa times the original capacitance without the dielectric inserted in here. And so that's sort of the net effect of what these dielectrics have. So they decrease electric field by the amount kappa, which is the dielectric constant of the material, and they increase the capacitance by the same amount, because now you can build up the electric field to be stronger, which means more charge can go on it, so you can store more charge at a certain voltage, at higher voltages, that is. So that's net effect about dielectrics. So try to walk away from the video with this reverse polarization effect that decreases electric fields, and that's the nature of how dielectrics are used in capacitors.